So now Cristian Tabares from the Institute of Fundamental Physics is going to talk about his work on variational quantum simulators, Waveguide-QED, and beyond.
Okay, well, thank you, Paula, for the introduction, and thank you also to the organization of this workshop, to the PEACE organization, which have done an amazing work this month, organizing a lot of really interesting activities. And as some of you may know, I'm Cristian Tabares from PHYSIC, and for the next couple of minutes, I would like to tell you a little bit about something that I've been doing in collaboration with these really nice people here, in which we have been exploring how you can get the most of current quantum simulators, and in particular, we have focused on Waveguide-QED. So this work has been accepted in PRL. If you're interested, you can just take a look here. Just to start, since we have a really broad audience, let me just get some really common points. Also, people previously have just discussed some of these topics and have introduced them amazingly. But just to set a common ground, I'm sure that most of you know what analog quantum simulators are, right? And these have in common the thing that they are able to mimic a given entire Hamiltonian, okay, using a controllable system, okay? So you have your analog simulator tuned in such a way that you can control its parameters and then mimic the Hamiltonian that you want to study, okay? This is, for example, you can have examples using collatons or trapez ions or different setups. And the thing is that with this kind of global control that analog quantum simulators have, you can lead to calculations that are more resilient to noise and errors, okay? And this is fine, but the problem is that in general, you can only simulate Hamiltonians whose interactions you can actually engineer, okay, in your lab using these controllable systems. So in order to get something more of this analog quantum simulator, we may wonder there's some different ways, and in particular, the people from quantum algorithms, the quantum algorithm community, have thought about a couple of things that can be done to explore and to obtain more of your device limitations, and these are variational quantum algorithms, which have been discussed very well before me, so I just assume that most of you know what they are, and in particular, you encode your problem in a quantum circuit, right, with some parameters, and you minimize given cost function that encodes your problem with the help of a classical computer. And this is cool because with these ideas, you can solve some of the limitations that these niche devices have, okay? But they have some problems that Halva has told you about before. For example, the appearance of barren plateaus, local minima, and different several things that make these variational quantum algorithms not be as wonderful as they may look like, at least at first sight. So with this setup in mind, what we do is try to combine both approaches, okay, and we try to apply this variational method to analog simulators. So these are variational analog quantum simulators, and the thing is that they have two really good advantages. First, you can use the many-body entangling operations that analog quantum simulators have, okay, and you can kind of use these global operations to obtain this large-scale entanglement, and you can also use some digital operations that increase the expressibility of your ansatz. But the most interesting thing here is that using the classical optimization loop, you can use the resources that you actually have available in a really much more efficient way. Okay, so the idea, like this picture, I'll just show a picture really similar to this before, but I really like the idea because what you have is that you have an initial state there, and you have then your target state, which is the state that you want to create, for example, the ground state of a given Hamiltonian, and you want to travel through your Hilbert space, okay, to create the target state. So in red, you can picture that line as the resources that you have. And what the classical optimizer does is telling you the most optimal way to travel through the Hilbert space to reach the target state that you want. So you don't really need to know a specific set of operations to create the target state, but instead let them be classically obtained using the classical optimizer. Okay, so this is the idea of this, and this has attracted the attention of of different groups recently, and in particular in this nice review there, some people much smarter than me propose that this could be a really nice way to obtain a practical advantage, a practical quantum advantage in quantum simulation. Okay, so this is fine, this is cool, but the problem with most of these approaches that I just showed you is that they in general consider a fixed range for the interactions. Okay, so the qubits speak among themselves in a given way. It can be an all-to-all interaction, but it still is in a given and definite way, and this imposes a fixed connectivity in the ansatz. So we may wonder if it is possible to also optimize this range of the interaction, okay, also optimize this connectivity. And in particular, the funny thing about this is that this tunable long-range interactions, this ability to optimize the connectivity between constituents, are naturally found in Waveguide-QED setups, which is a specific platform in which we can implement these ideas. So instead of considering general analog quantum simulators, what we do is that we consider Waveguide-QED setups that I will tell you about in just a minute. And then we, instead of building the general quantum circuit, we build a Waveguide-QED setup using these entanglement operations provided by the waveguide. So the idea here, let me introduce you to the topic a little bit, is that with these waveguides, you can obtain light matter interactions that generate tunable long-range interactions between the qubits. Okay, so the ingredients to obtain them are the following. First, we need the waveguide. Okay, this is the reason why it is called Waveguide-QED. Okay, so this waveguide can be a photonic crystal, can be a material, can be different origin. And the thing is that this is a periodic structure. And since it is periodic, it has a band structure, okay, and we can plot it like that, and that band structure has a bandage. Then we need a quantum emitter, which in the most simple way we picture as a two-level system with a ground state and an excited state, and there is a transition between these two states that is coupled to the electromagnetic field. So our idea here is saying, well, okay, we have a transition from the emitter to from the excited to the ground state. So when the emitter is on the excited state and goes down to the ground state, it emits a photon, okay, and we can place the frequency of the transition in the band gap. Okay, so the idea here is that when the emitter emits the photon, this photon cannot propagate through the waveguide because it cannot live in that waveguide. So since it cannot live there, it gets trapped, it gets bounded around the atom in what are called atom-photon bound states. So we get a photonic cloud around our quantum emitter, and we can understand the effective interactions between the emitters via this photonic cloud. So we have an overlap of the photonic cloud, and with this overlap, we can get the effective interactions between the emitters mediated by the waveguide. Okay. We can also include some lasers, okay, to our system that increase the tunability. Okay, we can, for example, turn on and off interactions, turn the strength, also tune the length of these bound states. And in general, the main thing that I want you to remember from these slides is that you can find these effective interactions between the emitters at the end of the day. Okay, you just adiabatically eliminate all these terms, and you finally get these interactions between the emitters, which are, first of all to all, okay, because here we can see that all the qubits interact among themselves, but they exponentially decay. Okay, so the amplitude of the interaction exponentially decay with the distance between the emitters. And the important thing here is that this exponential decay is controlled by a parameter L that can be tuned using your lasers, for example. So you can dynamically tune the length of the interaction and therefore the connectivity that I told you about at the beginning. So with this, we decided to build a Waveguide-QED ansatz to do a variational quantum algorithm that combines first the free time evolution under this interaction Hamiltonian, and we let both the time and the length of the interactions to be the parameters that we optimize. Okay, so we let the operation be the unitary generated by some of these Hamiltonians. Then we include single qubit rotations that physically can be done simply with a laser. Okay, and this increases the expressibility of our system, and this leads us to the Waveguide-QED ansatz. So we get first the waveguide interaction, then the single qubit rotations. That is a layer. They're in yellow, okay? And you stack D layers, okay? And that gives you more parameters to actually find the ground state or the desired state that you want, okay? With this, we studied as a first benchmark, okay, the ground state of different strong range speed models, in particular the XX set and the ISA model in the critical points, okay? And we use as a figure of merit the infidelity between the optimized state and the exact ground state that could be found numerically easily because the systems are really small, the system that we study. And we also compared the results with the state-of-the-art ansatz that Alba told you about before. Well, first you can have these problem-agnostic ansatz, such as the hardware efficient of the brick layer, also problem-dependent ones, such as the Hamiltonian variational ansatz, and finally, you can get your Waveguide-QED ansatz, let L go to infinity, then have an all-to-all interaction, and also study the effect of these infinite range interactions. Okay, so just with this, let me go briefly through the results, because I'm slightly out of time. So we first studied the infidelity between the exact ground state and the optimized one as a function of the number of layers, okay, as a function of the depth. And what we found first is that, well, the hardware efficient ansatz, as expected, had the worst performance because this is really hard to optimize, okay? So people, when they proposed it, as Alba told you before in this paper by IBM, by Kandala in 2014, they first proposed this ansatz and implemented it experimentally. But the thing is that it worked not that bad, but the problem is that as soon as you scale a system, this cannot be optimized. Okay, so this is the reason why you cannot get really good performance. Then you can turn to the brick layer ansatz, okay, which has some specific and particular properties. And in general, the bricklayer ansatz, in particular in the transversalizing model, you take a look at the simulation that for bigger systems, okay, the results are better, but you need some depth. In particular, the good results are obtained up to from up to X layers. This is due to something related with light cones that is well understood. And the problem with this is that you need to stack a lot of operations, a lot of CNOT gates, and this leads to problem when you want to actually implement it in a real experiment. Anyways, the Hamiltonian variational ansatz also works good, okay, it's better at short depths than the bricklayer ansatz, but also needed some depth to obtain moderate good results, okay? And this is also really well understood in this nice paper, you are interested. So the behavior is the one expected. And now we came to the Waveguide-QED ansatz, which obtains also good results, but what we find more striking is that these results are much better, especially at short depths. Okay, so you take a look at what happens with just a few number of layers. Okay, we see that we get much better results than the other type of ansatz. Okay, and we may say, well, okay, we have long-range interactions, and due to these long-range interactions, we obtain these better results at short depths because we have different distant qubits that can speak among themselves with a given with an increased interaction strength. But the thing is that when we take a look at what happens with the infinite range, in particular, take a look up there in the transversalizing model that it's a bigger system. Okay, the infinite range case is much worse. Okay, so this tells us that it is not only the fact that we have long-range interactions, okay, but also the fact that these interactions can be tuned, okay, in the range and in the connectivity, the thing that gives the power to the Waveguide-QED ansatz. Okay, so with this, also we could take a look at the minimum number of layers to obtain a fidelity above 99%. And what we found is that in general, these are much, and you study this minimum number of layers as you increase the number of qubits, you can see that in general the Waveguide-QED ansatz needs much less layers as you increase the qubits. Okay, we are also actually exploring what happens when you make this figure, the x-axis goes to much bigger numbers, even to infinity. This is something that we're exploring. We expect that in general you may find that the Waveguide-QED ansatz has an scaling that it's not linear, it's maybe logarithmic. Okay. We also took a look at the long-range IC model. I don't have time to go through everything, okay? But if you're interested, what happens when you go beyond the first neighbor model and study more complex models, we also took a look. And the idea in general is the same, that you can use the classical optimizer to obtain an advantage comparing with other type of ansatz. And with this, we may wonder what is next, okay? So the first that we're wondering right now is what happens with the optimal rates, as I just told you, when the system size is increased. So this is something that we're taking a look right now, simulating all of this instead of with a state vector simulation with MPOs. You can also wonder what happens when you try to capture the physics of more complex models, because the things that we look at are simply toy models, okay? So we're also looking at this. And finally, and this is the thing that I'm most interested with, is what happens when you modify the type of quantum emitter. So instead of using, for example, atoms or qubits coupled to a waveguide, you use atoms in optical lattices. So with this idea, you get the resources of your quantum simulator and try to get the most of them. So for example, if we use fermionic atoms, maybe we could study problems in quantum chemistry or quantum materials that could be interesting in practical applications. So with this, I just go through the conclusions very briefly because I'm out of time. So I hope to convince you that variational analog quantum simulators are a way to obtain, and promising a way to obtain practical quantum advantage, and the Waveguide-QED platforms can be useful for that. And with this is my group and my collaborators, and thank you for your attention.
Thank you, Cristian. Now, are there any questions?
Thank you. Thanks for the talk. So if you consider two-dimensional models, for instance, do you still stick to the waveguide, to the one-dimensional waveguide, and you just control the hoppings, or you use a two-dimensional system?
That's a really nice question. Thank you. And actually, we do not have clear what is the most optimal way to do this. We are exploring both proposals, because first, exactly, you can have a photonic crystal, and you have a 2D photonic crystal. You can get this an analog of these interactions in 2D. Okay, well, they decay with some Bessel function, but it's the same idea. So we're exploring first what happens when you do this in a 2D photonic crystal. The problem is that those physical platforms are much less developed than the waveguide ones, especially when you take a look at the people with what the people using superconducting circuits can do right now. They have waveguides of 20 qubits, well, not 20, but 10 to 15 qubits, and they can do really nice things. So that would be the second approach to say, well, okay, since we have long-range interactions, let's try to use these long-range interactions to map the 2D lattice to a 1D chain, and then try to exploit the fact that we have the long range. So we are not actually, don't have clear what is the most optimal approach, but we are exploring both of them. Thank you.
More questions? If not, we move on to the next last speaker of this session.